Welcome back, everybody. Shout out, Ellie, if you're watching. We'll see. Ellie, if you're watching, just walk in tomorrow and say, now nobody can say this, just say the word bananas. Just like before you even say hi to me, just look at me and say the word bananas, and I'll know you watched the video. All right. The code word. Nobody tell it. Nobody took it off. All right. So section 4142 review. Remember, the quiz is tomorrow. Yeah. Let's just get to it, shall we? For the following situations, decide whether the random variable x is discrete or continuous. Now, remember, discrete is whole values only, and I shouldn't even say whole values only. Ones that could have gaps or breaks, because I think about it this way: if you round it, and that's like this thing here. Part A: the weight of a person rounded to the nearest whole pound. Discrete or continuous? Discrete. Right? What if I had said rounded to the nearest half pound? Still discrete, right? So I struggle to say like, ooh, only whole values. Really, it's just, you cannot have repeating or infinite decimal values. Now, if I had just said the weight of a person, what's that turn into now? Continuous, right? Because I could keep narrowing down that weight. There's no gaps or breaks in weight. All right. Like part B here, the length of time it takes to drive to school. Continuous, right? This is continuous. When you're talking about it, you might say, oh, it's 15 minutes. You might say that it's like, oh, it takes me 15 minutes to get to school. But yeah, you're rounding that, right? And then part C here, the number of chairs in the student center? Discrete. Questions about number 1? Gonna go quick. That's okay. We'll have time to relax. Use the frequency distribution to answer the following questions about the number of televisions per household. I really could have made this TVs and households like part of this table here, but that's okay. Construct the probability distribution for the number of televisions in a house. Now remember, probability distribution relates directly to relative frequency, right? Relative frequency and probability distribution kind of are like the same thing, right? All right, so let's do TVs. And let's do the frequency here. 0, 1, 2, and 3. We've got 4, 15, 30, and 21. Okay, let's find the probability distribution. Excuse me. Okay, now when I say that, that means list out all the probabilities. P of 0, P of 1, P of 2, and then P of 3. Okay, if I randomly select a person, what's going to be the probability that I have gotten that they have 0 TVs? Well, it is the frequency divided by the total frequency. So let's add these up. 45 and 25. Is that 70? Did we get 70 as our N? So 4 out of 70 is 0.057. But let's round it. 0.06. P of X. 0.0. What did I say? 0.06. 0.06. P of 1, 15 out of 70, which gives me 0.21. I have a 21% chance of randomly selecting a person with 1 TV in their house. Come on. There we go. P of 2, 30 out of 70. Less than half. 0.43. I have a 43% chance of selecting a person with 2 TVs in their house. And then 21 out of 70 gets me 0.3. Really? Just 0.3? Yeah. Oh, yeah, divided by 7. 0.3, 3/10, 30% chance. What should the probability distribution all sum up to be? Yeah, 100% or 1, right? Good, there's my probability distribution, listing them all out. listing all the different probabilities that everything could have. Part B here, compute the mean of the probability distribution. You know what? Now I'm going to get my formula sheets because I'm going to read it right as you're going to see it tomorrow. We are in chapter 4. It says the mean of a probability distribution Oh yeah, sum of xpx. That's right. I was like, what? I couldn't find it there. xpx. 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 Okay. So what is x in this case? Right. Oh, it should be frequency, shouldn't it? Is it x? No, it's TVs. It's not frequency. It's TVs, right? Yeah, it's TVs. This is your random variable x, right? Where x is the. Did I say? Yeah, because this is like your probability of 0, probability of 1. Yeah. Okay, there we go. Second guessed myself there. So this is going to be 0. This is going to be 0.21. This is going to be 0.86. That is going to be 0.9. Yeah, because this is like my expected value, right? Like if I randomly chose a person, what do we believe their number of TVs would be? Well, it would be 0.21 plus 0.86 plus 0.9. 1.97 TVs. So mean is going to be 1.97. Yeah, that's this. That's my expected value, right? I expect a person to have just, probably around 2 TVs because that's my highest value anyway, right? All right. And compute the variance and the standard deviation. Well, for the variance and standard deviation, it looks like I've got to do x minus mu squared p of x. I have to write tiny, think small. X minus mu squared p of x. I'm going to sum that up, and then I'm going to, well, for the sum of that, I'm just going to, that's my variance. And then the standard deviation, I'm going to square root that. Okay, so I've got to go in and I've got to calculate all these little things here. X minus mu squared p of x. So we've got 0 minus 1.97 squared, and then times p of x times 0.06. 0.23. Okay, we're going to run that same calculation, but instead of 0, I have calculating 1, and my decimal here is 0.21. No, I lied. No, that's right, 0.21. 0.197, let's say 0.2. And then we're going to run that same calculation, now with 2 TVs, with a percentage of 43%, so 0.43. Ooh, small number. 0.000387. 4. There. We'll just round it to that. And then same thing. Now, why do we expect it to be so low right there? Why is that so small? Yeah, because it's the closest thing to the mean, right? And this is a measure of variance, a measure of deviation, right? And this is 3 TVs with a percentage of 0.3. 0.32. Okay, so I'm going to sum that up, and that's going to be my variance. So I've got 0.23 plus 0.2 plus 0.004 plus 0.32. 0.754. Okay, so my sigma squared is 0.754. So therefore my sigma 0.868, 0.87, whatever, 0.87. I round it to the nearest thousandth and then hundredth. I don't know what I'm doing here. 0.87. There's my standard deviation. And again, we know things based off of that standard deviation. Now we know that if the mean is 1.97 and my standard deviation is 0.87, I can now calculate 1, 2, 3 differences away from the mean and run my expected values based off of that too. Which is what we get into like in chapter 5. We can say, okay, if we know my mean is this and I know my standard deviation is this, what percentage of things fall between my 2 to 3 standard deviations? Then we can talk about like, okay, is this truly an outlier, you know? All right, taking a look here, number 3. For the following situations, decide whether the situation represents a binomial experiment. Okay, number 3A, you draw 3 cards, one at a time from a standard deck. You do not replace a card once it is drawn. The random variable represents the number of times you draw a heart. Yes or no? Binomial or not? No, not binomial. No. What makes this not a binomial experiment? Now, that point, okay, what is a success? What is a failure? So there's only 2 outcomes. You see what I mean? There are multiple ways to get a success, but there are still only 2 outcomes. I can either get a success or not.
It's the not replacement.
It's the not replacement. Right. That piece makes it not a binomial. You roll 3 dice 10 times. The random variable represents the number of times you roll a multiple of 2. Now, in that respect, what is it? That is binomial. You either get a multiple of 2 or you don't. A pitcher throws 20 pitches. The random variable represents the number of times the pitcher throws a strike. Binomial. Strike or not a strike? You know, I should be a little bit more specific because some baseball people might be like, well, what's the count? Is he going to choose to not throw a strike? Is he going to choose to make the hitter try to swing a bad pitch? You know, so I should have said within that problem, assume each pitch is independent from one another.
Like the probability of the strike isn't the same every time, right?
That's why I should have said assume independence. Right, his arm might get tired.
Or
His
the
arm
pass,
might
and then they don't hit it.
110
Throw a ball
pitches.
at-
Yeah.
Throw a ball at the catcher catches. And then
See, I always come up with problems in this. There's always like a little counterexamples. Like, there's always arguments to be made. All right. So I like sticking to flipping a coin, right? Rolling a die. There's less
This one's out of lead.
All right. Suppose a coin is weighted so that the probability of I want a weighted coin. You know, we come up with these examples of like weighted coins. I want a weighted coin. Anybody ever finds one? That's an end of the year gift that you could give me. A weighted coin or a weighted die. Yeah, like that. Suppose that a coin is weighted so that the probability of tails is 0.4. Answer the following questions, assuming that you flip the coin 15 times. Okay, now this is the binomial distribution calculation, right? Let me just move this down a little bit and write it up here. This is NCX P to the X Q to the N minus X. And that is just straight off the formula sheet, right? Okay, suppose that a coin is weighted. Yeah, and then the tic-tac-toe thing is the exact same thing. We're just doing different things here. Suppose that a coin is weighted so that the probability of tails is 0.4. Answer the following questions, assuming that you flip the coin 15 times. Okay, what is N then? No, what is N? 15, right? Okay, so in this case, I know that N is 15. What is X in 4A? 6. What is P? 0.6. Be careful. That's why I bold it. Because I could ask, so the probability of heads, in this case, a success is heads. So 0.6. Q is 0.4. Right? So now I'm running the calculation, flip exactly 6 heads. This is 15C6, 0.6 raised to the 6th, 0.4 raised to the what power? 9th. Right? All the leftover ones. All right, so I say 15C6, 0.6 raised to the 6th, 0.9 raised to the 9th. Oh, 0.4. Blech. Much better. Is my probability 90? Hope not. 0.06. 0.06. That is exactly 6 heads, right? So out of my 15 times, only getting 6 heads. What is the probability of flipping more than 12 tails? Okay, so the probability of x more than 12 is the probability of 13 plus the probability of 14 plus the probability of 15. You follow me there? More than 12 tails. And in this case, okay, so n is going to be 15. X is going to change for each one of these, right? X is going to be 13, then 14, then 15. I'm going to have to run 3 calculations here. But P is going to stay constant. What is P? 0.4. Therefore, Q is 0.6. All right, now, I'm going to put it all in the calculator as one calculation. So go with me here. We got 15C 13. And for this one, 0.4 raised to the 13th, 0.6 raised to the 2nd. Okay, I'm going to take that plus. The reason I'm doing that is because it's such a small number. So plus, same thing, 15C, but now I'm going to drop up, go up to 14 times 0.4 to the 14th times 0.6, now just to the 1st, right? Plus, same thing, 15C 15C what? 15. 15C 15, 0.4 raised to the 15th, and then it would be times 0.6 to the 0, which is just 1. Okay, so here we got it. 2.789 times 10 to the negative 4th. So 0.00028. Questions about that? Okay, calculate the mean, variance, and standard deviation. Super easy here. Super easy. The mean, remember this straight off the formula sheet. The mean is NP. The variance, sigma squared, is NPQ. Oops, NPQ. And then for my standard deviation, I would just square root it. So now, getting a tail, right? Pay attention to getting a tail. Okay, so that means my P is 0.4, right? So my mean is going to be 15 times 0.4. This is my expected value, 6. Okay, NPQ. So that's 15 times 0.4, or just mu times 0.6, 3.6. So sigma, square root it. Whoa. Square root it. 1.89 rounded up, 1.9. Make sense?
Yes.
All right. Basically the same type of thing now, just with a game of tic-tac-toe. In tic-tac-toe, games can end in a win, loss, or draw. Tac-tac-toe. It's a new game I've invented. Tac-tac-toe. Tic-tac-toe. Tic-tac-toe. Games can end in a win, loss, or draw. I wonder if it auto-corrected. Let's assume Mr. Laverick's probability of win is 0.4, probability of loss is 0.25, probability of draw is 0.35. I win more than I draw. Assume that I play 8 games with results being independent of one another. So that means I have binomial distribution. What is the probability that I win no games? Okay, so in this case, my n is 8. What is x? 0. Okay. What is p? Probability of win is 0.4. Right? So that's going to be 8c 0, 0.4 raised to the 0, 0.6 raised to the what? 8. Right? Would you follow me there? So therefore, I've got 8c0 times 0.4, which is just 1, because there's only one way to make that. Choose 0. There's only one way. Times 0.4 to the 0, which is 1. So times 0.6 to the 8th power. 0.017, 0.02. 2% chance that I win no games. What is the probability that I lose 3 games? Okay, so n is still 8, x is 3. What is p in this case? 0.25. 0.25. So that means I have 8c3.25 raised to the 3rd, 0.75 raised to the 5th. Okay, 8c3 times, whoops. I forgot 8c3. There we go. 56 ways. Times, I forgot my 56. Times 0.25 raised to the 3rd times 0.75 raised to the 5th. 0.208, so 0.21. 21% chance I lose 3 games. Probability that I win at least 2 games. Probability that I win at least 2 games. Now, the probability that I win at least 2 games, right? Isn't that the probability of 2 plus 3 all the way up to plus 8, right? That's a lot of calculations, right? What could I do instead? The complement, right? So it's 1 minus the probability of what?
Losing probability.
No, don't keep it with win. Keep it with win.
Probability of 1 and 0.
Right. So basically this, right?
Yeah.
Which, like just exactly what you said, probability of 0 and the probability of 1, which is way easier to calculate, right? So let's run those two calculations with n is 8. X is 0 and 1. What is P in this case? Probability of win, 0.4. Yeah, this is why I would I don't want you, I would discourage you from using loss, because are win and loss complements? No, because you can tie, right? So be careful of that. All right, so I've got probability of 0. Probability of 0 is 8 C0, which is just 1. Times, and that would be 0.4 to the 0, which is 1, times 0.6 to the 8. So we have this plus, and then we got to run the calculation for probability of 1. 8 C1 times 0.4 to the, it is right, first times 0.6 to the 7th. All said and done, 0.106, so 0.11. Now, be careful. That is 1 minus 0.11, right? That 0.11 was probability of 0 plus probability of 1. So 1 minus 0.11, 89%. .89. Which, I mean, your answer should be logical. What is the probability that I win at least 2 out of these 8 games? It's probably a pretty high chance, right? Because I win 40% of the time. What is the probability of tying between 1 and 3 games inclusive? Okay, so that is the probability of 1 plus the probability of 2 plus the probability of 3, right? Where n is 8. X is going to be 1, then 2, then 3. What is P in this case? 0.35, the probability of drawing. Okay, so let's run those 3 calculations and add them together. Okay, so the probability of 1. So that's 8 C1 times 0.35 raised to the first. Sure. Times 1 minus 0.35, 0.65. 0.65 raised to the 7th. Okay. You could round that. I'm just going to keep it going here. Plus, and then I've got to do the same thing. 8 C2 0.35. Oh, that's a negative. Don't do that. 0.35 to the 2nd times 0.65 to the 6th. Plus I forgot my 8. 8 C 3 0.35 to the 3rd, 0.65 to the 5th. Bingo, 67%. 0.67. That's the probability of drawing 1, 2, or 3 out of these 8 games. Pretty high chance, right? Because I've got a 35% chance of drawing. I'm playing 8 games. What's the probability that I draw 1, 2, or 3 games? Yeah, it's pretty high. On the higher end percentage. Questions about any of that review? Feel good about that now?
Yes.
Cool. All right, let me stop the video.
Tell her to say a different fruit if she watches the whole thing.
Oh yeah. Now,
Strawberries.
yeah, say
Peaches.
peaches. We'll go with peaches. So,
It's
here we
really
go.
good.
Say bananas and peaches.
Actually,
All right. Have a good day.
honestly like one of the best.